Thanks for joining and welcome to the edition 2 of our technical webinar, session 1. So good morning and good afternoon. We have, I assume, a large audience, very international from different countries. Let's say with this, it's 4 p.m. in Germany. So we are covering, let's say, mainly North and South America, plus European countries and Africa, probably some Middle East countries. So some of you know me already. My name is Florent Giraudet. I'm the sales manager of Tridelta Meidensha. I'm gonna hold this webinar today with Philipp Raschke from the R&D side. He's on the other side, looking at the let's say, to make sure that the webinar is running properly as a moderator. So the topic today is surge arresters, and more specifically some basic understandings and fundamentals about withstand levels, about altitude correction, and about clearances calculation. So these are actually important topics. You don't have to be a specialist. I will try to be, let's say, concrete. I will try to give some practical examples. And these are important topics because the outcome of this, let's say, technical understanding is to make your system, your substation, even your transmission line more compact. Also, the surge arresters, let's say, suitable for the need you have, and not to make it oversized. So this is, let's say, that's why we start with this session 1 on this topic, because this, let's say, we need to clear some doubts and misunderstanding about arrester configuration. So, and also it's important for us to have this kind of online meetings. As you know, it's impossible these days for most of our, let's say, in the business in general, but also specifically the high voltage industry, to have the chance to meet in person and also to see us in the exhibition and congress. So it's important for us to somehow reconnect due to this global pandemic. Before I start, important point, if we please send us questions. Philip is going to read the questions. He's going to follow up. It's important you write your question in the Q&A session, not in the chat. So Q&A, question and answer session, please. Okay, let's go. So before we jump into the topic, I would like to give you an overview of what we are planning. So let's say this is a general schedule, general plan for the next months. We would like to continue with these technical webinars. Let's say it has been quite successful so far, and we always get interesting questions from the audience, and also, as I said, it helps to reconnect and to, say, continue discussion on surge arresters and technical topics, also on projects. We had some interesting, let's say, feedback from the edition 1. And we decided to repeat this session also to address a different audience from the, let's say, from the Americas, with a different time zone. So this is one of the reasons. So we are planning in January, also an important topic that has been asked from many people. And this is, I would say, a large topic that covers the arrestor selection, how to configure a surge arrestor. So it's something important. We had many questions about it, and it covers many aspects, electrical and mechanical configurations. So, and then as you can see, for February, we are planning, let's say, a specific topic on residual voltage, protection levels. We're going to talk a little bit about this today because, of course, it's important. It's the main feature of the surge arrestor, but we'll not go into the details. As you can see, for session 4 and session 5, it's open to proposals. We are, let's say, we are listening to you. If you have any topic that you consider important, we will collect all the ideas and define those topics for March and April. Okay, this is the agenda for today. So as you can see, as you will see, those topics are related. So these are not separate topics. So installation withstand for the arrestor housing, clearances, altitude corrections, or somehow all related together, because there is often a misunderstanding when, let's say, when designing surge arrestors. We will take, depending on the time. Let's say if I manage to finish on time, but at least we'll have 20 to 30 minutes to go through the questions. And I rely on Philip to look after the Q&A session. So main topic, first topic, we will start with installation withstand on arrestor housing. First, we have a look on the IC 671-1, which is, let's say, the standard installation for a high voltage equipment. And then we will have a focus on what's the difference with the surge arrestors based on the IC 699-4. Okay, so let's start with, let's say, a concrete case or a concrete issue that surge arrestors manufacturers are facing. Basically, you have a specification that defines the ratings for the surge arrestors. Often at the beginning, you have the basic installation level, the BIL, which is based on the IC 671-1, and this applies for the system. So it's very common to see in arrestor specification the same BIL, so which is the lightning impulse withstand voltage. So the same requirement is often applied for the housing of the surge arrestors. And this is actually an issue because it can make the surge arrestor oversized. And of course, I will show you some examples. Of course, it will make it more expensive. And sometimes you will also need, depending on the voltage level, you will need a grading ring or additional, let's say, accessories, just because the length of the housing is too high. So just to make sure we understand about the wordings and the terms, when we talk about installation withstand of an arrestor housing, we want to demonstrate that the external insulation of the arrestor housing can withstand lightning, switching, and poor frequency of a voltage without any electrical breakdown. So I think this is a pretty common understanding here. And here you have some concrete examples about the installation withstand tests in the as per IC 699-4 performed on Tridelta surge arrestors. And you can see a typical configuration with a grading ring, two different, let's say, scenario where you have a direct line to ground breakdown or a flash over from the line to the intermediate flange and then from the flange to the ground. It's important to keep in mind for the, let's say, for the next slides, that when you do such tests, according 8.2 of the IC 699-4, we always perform the test on the housing. We never use a complete surge arrestors with metal oxide varistors. Otherwise, this will never flash over. So this is, let's say, a good example to explain the topic of the residual voltage. So in the IC 671-1, so I'm going to refer to these standards often today. So basically, it's going to be this one for a standard installation withstand. So you have some basic tables for standard installation withstand, switching, lightning, power frequency. And also in the next session, we will talk about the clearances. And you also have recommendation about clearances in this standard. So as you can see on this table, for each voltage level, you have different recommendation and standard values. But it's important to read, to go a little bit more in details and to look at the paragraph 5.5, selection of the rated installation level. So basically, for equipment to be used in normal environmental condition, the rated installation level should then preferably be selected from table 2 and table 3, corresponding to the applicable highest voltage for equipment, such that these rated withstand voltage are met. But, and this but is important because it's not often considered, for surge arresters, the required withstand voltages of the insulating housing are based on the protective levels, on the protection levels, which is the residual voltage. So often called in the standards UPL for lighting and UPS for switching, with suitable safety factors apply on the equipment. In that case, the IC standards for surge arresters 699-4. In general, therefore, the withstand voltages should not be selected from the list of 5.6 and 5.7. So why we should not, let's say, why we should not select from the list? Why this standards is not applicable for surge arresters? Because surge arresters are unique in a way that they are self-protecting devices. As you know, the active part of the surge arresters are called metal oxide varistors or zinc oxide resistors. So those internal resistors have inherent properties to limit the voltage across the terminals, across the arrestor. So, and this is the protection level, or often called residual voltages, or in the IEEE discharge voltages. So due to this self-protecting nature, the arrestor housing can have lower withstand voltages than the rest of the system. For these reasons, arresters do not have a standardized installation withstand rating. And therefore, you have a test in the IEC 699-4 for the design and testing of surge arresters to verify that the housing will not experience any external flashover under anticipated transient condition that may occur over the life of the surge arrestor. So this is, say, the conclusion of the first step. Always refer to the protection level or the residual voltage, because this must be coordinated with the lightning impulse, switching impulse, and power frequency withstand voltage. So now we have a deeper look into the arrestor standards in the clause 8.2. The calculation, it says quite simple. So you can see here the test voltage for lightning impulse withstand levels. The test voltage should be equal or higher than, well, actually in that case, 1.3 times the residual voltage at nominal discharge current. So the factor 1.3 is coming from a standard altitude of 1,000 meters. And we will come to the altitude afterwards. So you will see that for installation level, installation withstand, and also clearances, we will each time include the altitude correction. But we will cover this more in details in the third session. So basically, 1.3 times the residual voltage for a standard altitude of 1,000 meters. This is what you need to consider for the withstand voltage of your arrestor housing. Then comes Similar calculation with switching impulse withstand test. So above 245 kV system, we are considering switching impulses, and below 245 kV system, we're considering power frequency. So we can say that up to 245 kV, I would say most of the time, the lightning impulse or the lightning over voltages are the most important or the decisive dimensioning factor for the housing of the arrestor. So you can see here a similar calculation. So the test voltage for switching impulse withstand should be 1.1, so 10% the protection level times the altitude correction factor. And then comes the power frequency withstand voltage test. I'm not gonna say, we're not gonna talk too much about this because this is not a dimensioning factor, which means that the required value will always be lower than the lightning impulse. But similar calculation, but in that case, we are not considering the residual voltage because let's say a power frequency voltage is a continuous voltage and is not considered as an impulse, as a current impulse, so there is no residual voltage associated to this directly. So to summarize, the formula or the calculation is quite simple. The required voltage should be equal or higher than the stress. So in that case, the stress is the protection level of the metal oxide varistors, plus a safety margin, plus the altitude correction. And that's how you verify this. So here's a concrete example, an application case for 420 kV system with an altitude of 1,000 meters. So for this case, we took a standard configuration from Tridelta surge arresters, SBKT. We have a rated voltage of 336 kV, and we have a protection level at 20 kA for 871 kV, and a switching value or switching impulse residual voltage at 702 kV. So when we are applying this formula that we have seen on the previous slides, you can see that we have those results here, which are different than the insulation width and voltage as per 691-1. And actually, and obviously, they are much lower. So this is important to be considered. As a recommendation, I would say you should not, if you have to make a specification for surge arresters, you should not specify yourself the withstand voltage of the housing. This is the responsibility of the manufacturer to design, to test, and to release a product that is, let's say, performing according to the requirements. And those requirements are the system and the protection level you are giving. So most important is to define the protection level and not, well, actually, I'm not going to go into the details of the arrestor configuration, but to make it simple, most important is or let's say the most challenging part in the arrestor configuration is to select the right protection level, so the right residual voltage and the right energy ratings. But maybe we will talk about this in the next session in January. So as a conclusion, this 1,133 should be the minimum recommended value. Okay, so this is the, say, a summary for the first part, insulation withstand. So as a conclusion, surge arresters have unique non-linear characteristics thanks to the metal oxide varistors. They protect themselves, and of course the equipment, but they also protect themselves first. So you should always refer to the reserve voltage. Let's say those ratings, protection level and reserve voltage, those ratings are the key ratings for installation coordination. Then the external installation withstand capability of the arrestor should be demonstrated according to the surge arrestor standards in paragraph 8.2. And as I explained before, it's very important, let's say, to understand the concept that when we go to the test lab to perform this installation withstance test, the arresters are filled with insulating material. We are not using surge arresters with active part, otherwise the surge arrestor will never flash over. And just a note, because this has been, let's say, a common understanding in the last decades, let's say, there will be a statement introduced in the new IEC, but also IEEE standards that say that it should be noted that the impulse withstand levels of arresters' housings are not to be compared to BIL or CFO levels of insulators. Due to the arrestor's self-protecting nature, the arrestor housing can have a lower withstand voltage than the rest of the system without any negative impact on the system withstand voltage. Also, for these reasons, arresters are used in standard application generally don't have standard insulation withstand ratings. Okay, then the next part, we go to the clearances. So I really like this topic because I think there is, how we call it, kind of untapped potential. It's, let's say, an important understanding, but if you can go further and design your system more compact. And I will try to give you some concrete examples. So first we will, let's say, look at this IC 671-1 and -2 that explains, let's say, the standards, standard that defines the standard values, and then we will have some calculation examples for specific surge arrestor configuration. And maybe this will give you some ideas for your system. So clearances are important. So we are talking about face-to-face clearances. We are talking about face-to-earth clearances. So which is, let's say, important for the substation, for the design of the substation to avoid flashover on external insulation. So basically, the clearance, which is the arcing distance for an equipment. So let's say if you do the part one, the insulation withstand voltage, if you make the configuration properly on the surge arresters, then we are not talking about the equipment. We are only talking about as you can see on the picture, we are talking about clearances, like say potential clearances issues on the substation between two equipments or between, say, the equipment or the structure. Typically, you see on the left side a grounded structure. So typically the arcing distance, the insulation level for the equipment can be done in the factory, in the test lab. So we are looking at let's say, at your system in that case. So and of course it's not possible to do a complete test for a substation or for a system. Therefore, we need to make assumption and to make calculation. That's why the IC 671-1 is giving you some standard clearances to be applied in the substation. So this is the let's say the standard process according IC 671-1. So as you can see, there are different steps. First, we want to determine the stress, the over voltages that can occur on the system. So typically in that case, let me switch this. So typically in that case, power frequency, lightning impulse, switching impulse that can occur in service. Step 2 is to define the Western voltage to reach the expected failure rate, so which means the stress plus the safety and coordination factor. Then we integrate the altitude at, let's say, atmospheric or altitude correction factor. And then the IC 671 will give you some standard values in tables to select the appropriate standard width and voltage and standard clearances. So the concept is, let's say, very basic. You have a voltage stress. It's mainly coming from lightning and switching. Based on the stress, you define standard width and voltages, and based on the standard voltages, you define minimum clearances. So it's very common in substation to have those clearances the same as, I mean, the clearances of the surge arresters are often defined in the same way for all the equipment, for all the substation. But in some cases, smaller clearances are required. Typically, as you can see on the screen, on this picture, surge arresters above a certain voltage level are equipped with a grading ring. And sometimes you can have some physical constraint due to the ring. So it's often, let's say, asked if the clearances, so the minimum face-to-face clearance, in that case, between two rings, if this distance can be reduced. And of course, if you have a closer look at the surge arresters, considering the residual voltage, it's possible to consider a reduction of the clearances. But we can even go lower, and this is actually what I would like to highlight today. You can use, let's say, this unique feature of surge arresters, because they have this self-protecting nature, to decide on purpose to make your system more compact by reducing clearances. So the approach for the arrestor configuration, so we will go into the details. I don't need to, let's say, to repeat myself here, but basically the reduced clearances are defined in the Annex F. And this is, let's say, often an issue in IEC standards. Correct me if I'm wrong, Philip, but not everybody is reading the annex. So it's important to have a closer look on the Annex F, because there is actually a potential to make your system more compact and the clearances shorter if you're facing some physical constraints. Yep. So let's say the process is quite simple. Step 1, we will calculate the minimum clearance based on lightning impulse. Step 2, we calculate the minimum clearance based on switching impulses. And for the final definition, we are using the most restrictive one. So this will depend, of course, on the system voltage. An important note here is that the higher the voltage and the higher, let's say, the higher is the difficulty to reduce the clearance for face-to-face. And the reason is that when you are doing a calculation face-to-face, you are considering the lightning impulse on one side or the switching impulse on one side, and on the other face, you need to consider the peak value of the system. So, which is you need always to consider the worst case scenario. So here's a concrete example, and maybe you can see some relation from your system that you can maybe compare. And feel free to contact us after this webinar session if you have if you have a different system, or if you would like some support to make this calculation. We will share the presentation for sure. And yeah, so let's take a concrete examples. We have here a system of 550 kV maximum face-to-face voltage with an altitude of 200 meters. This table 2 and 3 in the IC 671-1 is giving us some standard values. And we're gonna try to calculate these reduced clearances based on the protection level. So step one is to determine the representative of a voltage URP, which is 1000 kV. So you can see here in the table, this is coming from the surge arrestor data. So this is the residual voltage at 20 kA discharge current, 1000 kV. So we are in the step 2, we are applying a safety and coordination factor coming mainly from the, let's say this 15% is a kind of safety margin, considering the probability of having higher discharge current than nominal. Then we have this UCW of 1150 kV. Then we go to step number 3, where we have to apply, and this is important, the altitude factor. Sorry, the altitude correction factor. In that case, we have only 200 meters. And therefore, there is a very small difference between step 2 and step 3. So we have now the required width and voltage, URW, of 1179 kV. Then, because we are talking about lightning, the IC 671-2 is giving us, let's say, a linear characteristic to define the clearances based on this required width and voltage. So there is a ratio, actually a ratio of 2. So for 1179 kV width and voltage, we need a clearance of 2.39 meters, let's say. And I would like to also to highlight also the importance to have a closer look at this calculation, and especially at the altitude. In the last session, in a few weeks ago in November, we had a question from Netherlands about having substation at sea level. So this makes a lot of sense, actually. Basically, if you're having your system at sea level, you have, let's say, more potential to reduce clearances in comparison to, let's say, a system at a high altitude. Okay, then I'm going to the next step for the phase to earth clearance based on switching impulse. So I'm not gonna, let's say, repeat myself. The principle is very similar. For the step 1, you are looking at the protection level. So we are taking 826, which is the residual voltage, the switching impulse residual voltage. So as you can see, as per the IC standard for surge arresters, the wave shape and the amplitude is different when it comes to switching. So then you apply the coordination factor. Let's say the safety margin or the factors are slightly different, but the principle is the same than for the lightning. Then for the step 3, you have the altitude correction factor to define the required width and voltage. And then again, we go to the tables in the IC 671-2, and we look at the recommended clearance for a specific required width and voltage. That gives us a clearance of 2.73 meters. So a conclusion for the phase to ground clearances. We are considering the worst case. Let me just to make sure So we are considering in that case the most, let's say, the most critical over voltage, or the most decisive dimensioning factor will be the switching impulse withstand voltages, which makes sense actually for a voltage of 550 kV. So we have the possibility to reduce the clearance originally recommended of 4.1 meters to a value of 2.75 meters. This is a significant improvement. And this is, let's say, now another example. I will, let's say, go a little bit faster to make sure you don't fall asleep with all this formula. So when now we go to the reduced calculation face to face, so you will see that there is a slight difference, yeah, because typically we need to consider the peak value of the opposite phase, let's say. This will have, let's say, an important impact. So for the determination of the required withstand voltage, the worst case voltage stress for lightning impulses for a face-to-face insulation will occur if one phase is affected by a lightning over voltage while the pole frequency voltage of the adjacent phase is at its peak of opposite polarity. So you can see the formula, how to define this value here, and this is coming from this value is coming from the previous calculation. We are adding, let's say, the peak value of the opposite phase, and then we define still the same process, going to the table in the 671-2. We define the minimum clearances face to face based on lightning. So now the same process for the switching. So let's say I'm not going to describe everything, but you can see that recommended value is 4.1 meter for rod structure. And in that case, it's a little bit more challenging because of the opposite phase to reach, let's say, to achieve a significant improvement in comparison to 4.1 meters. So we can reach, in that specific case, 3.95 meters. So we have to round up a little bit the value. So as a conclusion, you can see that for face-to-face clearances, improvement is not really significant, but still it is possible to reduce it from 4.2 meters to 4 meters. So summary for the clearances topic. Substation must be designed to avoid flashovers of external insulation. The IC 671-1 and -2 defines those minimum clearances to ensure sufficient insulation withstand and in general with a significant safety margin. It's often required to reduce those clearances during installation due to physical constraint, typically for the coming from the grading ring of the sub-arresters, but it could be for different reasons. So a reduction of the clearances is possible by looking at the residual voltage, and the calculation method is defined in the Annex F of the IC 671-2. And it's always, let's say, the same concept. Look at the protection level to define the most optimized settings. And of course, this will also depend on the national safety regulation. It's also happened that each country or each public utility has its own safety regulation. So it's of course important to look at it. But in general, national safety regulation are related to this IEC standards. So this is in general very conservative. So, and I think the most important part of the let's say of the conclusion is really to think twice when you are doing a system design or when you are defining the clearances for a substation or for a transmission line, it's always possible to improve the residual voltage and the protection level of the surge arrestor. If you look at our catalog, or if you look at any surge arrestor manufacturer, you will see in the brochure, in the catalog, some standard values, which are, let's say, very common for a specific voltage. But it's important to look at the different possibilities. There are plenty of possibilities to reduce the clearances, to reduce the residual voltage, which means a low residual voltage means a better protection level. So, and this is actually possible. There are plenty of possibility. If you're interested, you can contact us. It's also important, the easiest way to reduce the residual voltage is, of course, to reduce the rated voltage of the arrestor. But of course, this has then an impact on the temporary of a voltage performance. So you want to make sure that the arrestor can withstand the temporary over values of your system, the TOV values. And of course, you can use different size of blocks. Typically, if you go to a 245 kV system, you're gonna have a MOV block with a diameter of between 50 and 65 millimeters, let's say, depending on the requirements. But it is possible to use larger blocks, which are normally not used for this voltage level, but that can provide much better protection levels. And then we have also, let's say, as a manufacturer, we can make also a recommendation if, let's say, compaction is an important topic in your case, or clearance reduction. So feel free to contact us in that case. Just looking at the time. Okay. So next topic, altitude correction. So you've seen that we have already considered altitude correction for clearances calculation, or for insulation withstand calculation for the arrestor housing. So the idea here is to have a special focus on the altitude correction, because it's also common, let's say, a typical misunderstanding or a typical issue that we are facing in some countries with very high altitudes, for example, in South America, where sometimes you have to guarantee the performance of the arrestor for 4,000 or 5,000 meters. It's very common to see in the specification, let's say, ratings which are, let's say, oversized. And actually, this has to do also with the insulation withstand. This is more or less the same topic, just specific focus on the altitude correction, with a, let's say, a concrete example at the end. So, as I said in the previous section, we have already considered this altitude correction. The background is, I think, is understood by most of the specialists in the audience. The electrical withstand strength of an air gap depends on most generally depends on the air pressure, and the air pressure depends on the altitude above sea level. So the higher is the altitude, the lower is the air pressure, and the lower will be the electrical withstand strength of the air gap, so of the arcing distance in that case. So the I still again the same IC. So this IC actually is quite important when it comes to those installation coordination topics. This IC 671-2 defines altitude correction factor, Ka, to be used when determining the required withstand voltage. So typically when you do a test in a lab, factory, you are considering a test at sea level, and you need to apply this altitude correction factor to guarantee your equipment. And most of the time, the equipment is, if I'm not mistaken, actually depending on IC, I know there is difference between IC and IEEE regarding this topic, but typically for IC, it's 1,000 meters. So all the ratings which are standardized for high voltage equipment are done at 1,000 meters. So the calculation is quite simple. If you have altitude of 1,000 meters, the installation withstand of the equipment needs to be tested with 1,130 kV at sea level to ensure a withstand level, or withstand level of 1,000 kV at 1,000 meters, and the same, it's a similar calculation at the 3,000 meters, where you need to test at 1,445. So what does it mean for a surge arrestor up to 1,000 meters? So you can see here an example of calculation for a surge arresters with a protection level of 1,000 kV. So we are talking about lightning impulse withstand voltage. So typically this is a typical residual voltage for 550 kV system. Similar example as we had before for the clearances. So you can see the calculation. Let's say the required lightning impulse withstand voltage is the protection level at nominal discharge current times 15% times exponential the altitude divided by 8,150. So you can see here what should be tested to guarantee or to ensure, let's say, the performance up to 1,000 meters. So you need to test 1,300 kV lightning impulse. Now we can have, let's say, a different approach for a similar arresters. So what we are trying to do here is to take a typical arrestor configuration. So which, let's say, a normal creepage distance, a typical configuration that you can find in a catalog, and to look at the maximum altitude for a specific design. We have here the same protection level as before. So it's in that case, we took a surge arresters with a rated voltage of 420 kV, so for 550 kV system. So you can see that the lightning impulse residual voltage is 1,000 kV, and the switching impulse residual voltage is 826. So similar values as before, just to keep the similar examples. And now you can see that by doing the calculation with the standard surge arresters, if you make the calculation with lightning, you can install the surge arrestor up to 4,300 meters. And if you look at the switching, you can install it at 3,040 meters. So of course, we take the worst case scenario, and in that case, we will guarantee the arrestor for proper performance or proper operation at 3,040 meters. And this is important because in general, when we make a brochure or a catalog, we always specify 1,000 meters because it's quite difficult or challenging to specify a value for each type or for each configuration. But you have to keep this in mind that there is a huge safety margin for surge arresters when it comes to altitudes. So typically, for most of the system voltage, so it will depend, the higher is the system voltage, the more difficult it is. But typically here you can see that a standard surge arrestor for 550 kV system can be installed up to 3,000 meters. And I have another example here. Let's say some concrete facts about a similar example we had in South America for 245 kV system with an altitude of 4,500 meters. So in the specification of the client, there was an, if I remember very well, I should have written this. So on the right side, here, you see what we would have to configure, what kind of a surge arrestor would be needed if we have to respect, it's a standard hacking distance that is specified by the clients for the transmission line or the substation for this altitude. So it makes sense that you define a minimum hacking distance for your system, for the insulator strings of the transmission line or for the substation, and that you require this hacking distance for all the equipments. It makes sense. Yes, but not for surge arresters, as we explained before, because you have the protection level. And here is a good example. What is the consequence? So on the right side, you see if we want to fulfill this this minimum hacking distance, I think it was in the range of 2,400 millimeters. We need to use a longer housing plus a corona ring, actually, because if normally we would not use the grading ring, not the corona ring. We would not need a grading ring at this voltage level if the arrestor is compact. But if you increase the height of the arrestor, you will influence the voltage distribution along the MOV column, and this will require the need of a grading ring. So it means that this will reduce the hacking distance, and you need again to make the arrestor even longer. On the left side, you can see a compact design for 4,500 meters altitudes. And actually what is interesting is that this is a catalog value, which means that this is a standard configuration. So for a standard arrestor configuration. So which means that if you go to a catalog, if you select a surge arrestor with 228 kV rated, the standard value of the arrestor can be used for an altitude of 4,500 meters. And this makes a big difference. You see that on the right side, the arrestor is 1 meter longer, and the weight also is about 20 kilos difference. And for example, if you want to use it on transmission line to improve the lighting performance on transmission line, sometimes the clearances are an issue because you would like to integrate the arrestor on the cross arm, and you need to make it compact. So always refer to the residual voltage, and don't specify hacking distance for such arrestors. But you have to mention the altitude, and you have to make sure that the manufacturer guarantees the performance with this altitude. Okay, so it's almost 1 hour, so the timing is more or less correct, I would say. As a general summary, so this is just repeating myself as a conclusion. Always remember that surge arrestors are unique because they have a self-protecting nature thanks to the metal oxide varistors, to the zinc oxide. Those protection level, those residual voltage, which are coming from the, say, non-linear characteristic of the metal oxides, are the key characteristic of the surge arrestors. So it makes sense that we are using the full potential of the arrestor when we make a design, a substation transmission line design. So as per IC definition, minimum withstand levels of arrestor housing must be calculated from the protection level. There is no need to specify the same insulation level as the substation equipment. It will make it oversized, it will make it more costly, and you could also face some physical constraints. Depending on national safety regulations, you have the possibility to reduce the clearances of the surge arresters, face-to-ground clearances, or face-to-face clearances, considering the protection level. The altitude correction factor needs to be applied on the protection level, including coordination factors, to determine the minimum withstand level of the arrestor. So if you have any concrete case, you can contact us, and we will try to support you in this calculation. So now it's time for questions. We have about 30 minutes.
Okay, Florent, at first, thank you for that very revealing presentation. I think it was interesting and very clear. I could follow up very good on what you told. Meanwhile, there have been some questions raised by our audience, and some I have answered already, and some I have left open for you. So if you please, I would go through the questions and maybe you can have some answers on that. Let's begin with one of the first questions. There was somebody asking, it was the first part of your presentation, insulation withstand of arrestor housings. And I think there was a question concerning your wording. The question was, shouldn't that say that the arrestor housing can have a higher withstand level than the surge arrestor itself, not lower? And I think this is concerning the insulation level compared to when you test the insulation withstand, compared to a surge arrestor with MOV blocks. Do you understand the question same like me?
Can you try to translate with your own words?
I'm not pretty sure. Maybe we have to ask. Shouldn't that say that the surge arrestor housing can have a higher withstand level than the surge arrestor itself? It's the first question. You can read.
Just switch off the microphone.
I know Vincent Green, so I will maybe get back to him to understand a little bit more the question. So when we talk about the surge arrestor itself, I'm not sure really to understand the meaning of the question. So if I try to summarize based on my understanding, as you can see in this slide, on the right side, you have the what you see in green represent more or less the active part, so the metal oxide surge arresters. Based on the height of this active part, we will define the maximum residual voltage of the arrestor, and we want to make sure that the housing, so the external housing that you see in brown, is properly dimensioned, not to flash over with considering the maximum residual voltage, including a safety margin, because you might have sometimes higher discharge current than the nominal, and of course including the altitude correction factor and coordination factor. Yes, and then when it comes to the substation itself, of course, this is a little bit, let's say, more challenging, and we need to, let's say, to check case by case. It also depends on the protection distance from the equipment. But in theory, if, let's say, the calculation from the protective distance is done properly, you should be able to have the same withstand level for the rest of your equipment in the substation, I mean the same as the harvester housing. But this needs to be checked, of course, because it will depend on the distance, let's say the installation distance from the equipment to the surge arrestor. So there is a question from Rodel Hernandez. Is that correct? I go through the question from top to bottom? Or you want a different?
You can do it like this, of course.
There is a question, well, maybe you know better than me. This constant number coming from the exponential factor of 8,150 in the altitude correction formula. This is a constant number. Yes, it is. Where it is coming from exactly, I would need to investigate deeper.
Well, it has something got to do with the statistical behavior of flashover. You are calculating a security factor with that equation, right? And with that 8,150, with this factor, you are also involving statistical behavior of the flashover. But this has been done before the surge arrestor standard has been released, so this is not described. But sure, there is like a scientific investigation before to find out which factor you have to apply for the statistical uncertainty. So yes, it's a constant number you have to consider in the altitude correction.
Okay, I take the next question from Ian Koroselev. What is about insulation withstand in polluted areas? So maybe I can take this example. I think on these slides we have let's say a better view. The pollution level, or let's say the contamination, does not have a significant effect on let's say on the surge arresters. Maybe Philippe, you can provide more information. So basically, when we have a high contamination or some, let's say, extreme polluted condition, we need to look at the creepage distance, because the problem is the surface current on the external housing. And as far as I know, there is no, let's say, significant relation with the pollution, only with the, let's say, the atmospheric condition. Yeah, when you do, typically you do switching impulse withstand test and power frequency withstand test in wet condition. So depending on this, of course, the salinity of the water or things like this, you might have let's say a different behavior than in the test lab, but no significant impact. So
yes, you're right. So on one hand, you have to make sure that your surge arresters applies for the pollution zone you are installing it at, and you have to make sure that the surface current is not so high that the surge arrestor will flash over on the surface due to a rising current and conductive layer. And the other thing is the insulation withstand of the air itself, and therefore we test under dry conditions and we test under wet conditions, because the conductivity of the air is different if it is wet. But normally we are distinguishing between the creepage distance and pollution level and the insulation withstand of the surge arrestor. So it's two different things.
I'm just taking a quick questions from Vishnu K. Which IEEE standards deals with altitude correction? If my memory is good, it's C62.22 and 11, but both actually. So C for the surge arrestor, C62.11 and C62.22. Another question from Juan Manuel. The same concept and theory can apply to non-gap line arrestors. Yes, of course. Let's say that this concept is, let's say, more specific for transmission line. Because let's say externally gap line arrestors have shown better life expectancy over the time. Some utilities are a little bit reluctant to apply on each phase and each tower on the complete system non-gap line arrestors, so which are directly connected from phase to ground. The main reason is that mechanical failures has been a challenge for many years. So, but definitely there is, let's say, this is probably one of the major evolution in the future of transmission line. I take the question from Thomas Colasanti. Altitude correction factor calculation used here seems different from the use for bushings correction factor, as in this case, the correction applies only for altitude above 1,000 meters. Can you confirm? Well, I don't think there's a difference. Maybe there is a small confusion when we go to these slides. Let me jump to the right slide. Up. Typically here, yes. So when we look at this slide, the blue curve that you see is actually using exponential 1,000 minus the altitude, because we are specifically interested to know, let's say, the required lightning impulse withstand voltage for a specific altitude. But the graphic could be confusing, yeah. But the same concept applies to the bushing. This is actually interesting because, do we have an example, a picture here? I don't know if we have a transformer, but typically if we, well, this is a bushing, but not a transformer bushing. This is let's say a line underground cable bushing. This also makes a lot of sense when it comes to transformer protection, that there is also a possibility to look at the insulation level of the bushings. And sometimes you have a difference between the, let's say, the BIL of the windings of the transformer and the BIL of the bushings. But basically, I would say that there is no, let's say, serious consideration of the arrestor protection level when it comes to a final design of the bushing. So I'm not a specialist of bushings, but as far as I know, the BIL of the bushings are the same as it is in the substation. But very often, in majority of the cases, as you can see on this picture, but as you can see on the typical power transformer application, the surge arrestor are directly installed next to the bushings. Therefore, it means that it makes sense physically to, let's say, it is possible to reduce the insulation level of the bushings the same value as it is for the surge arrestor. Okay, go to the next one. From Fernando Ramos, applies the use of altitude correction factor when the surge arrestor will be installed on installation less than 1,000 meters. Yeah, so typically, if you make this calculation with, it's difficult to see my screen at the same time, so oops. So if we look at this this example here for the clearances, here the altitude is 200 meters. So when you calculate the exponential value with an altitude of 0, you will get a factor of 1. So basically, it means that it's quite important, because if you consider, let's say, an installation at sea level at 0 meters, it means that your altitude correction factor will be 1, and that the required voltage for the minimum clearance will be actually the residual voltage times the correction factor, the coordination factor, including, let's say, safety margin. So yes, this makes a lot of sense. And most of the equipment that you see on catalogs, not only surge arresters, but many equipments, have Western values for an altitude of 1,000 meters. So if you are interested in clearances reduction, and that you have a system at the sea level, you can have further reduction. Okay. Just interrupt me, Philip, if you want to add something, or if I say something wrong. Next question from Marino Gastoncecchi regarding the altitude correction. When defining equipment for installation above 1,000 meters, the usual issue is that we have the lighting impulse Western level and the switching impulse Western level of the equipment at sea level. And the question is, if we only have this data, the correction should be done in the same manner. The question is because the lighting impulse Western level and the switching impulse are not the coordination of a voltage defined in IC 671. So I'm not sure if I understand the question properly, Philippe. So if we have, let's say, if you have, let's say, a standard equipment, this is designed for installation up to 1,000 meters. For installation at higher altitudes, the manufacturer of the circuit breakers pushing surge arresters should confirm the performance at the required altitudes. If not, they have to use longer housing, right? So in that case, you are applying when you have tested your equipment in the test lab, you have performed a test at sea level, and you have applied an altitude correction factor to guarantee the value as standards for 1,000 meters. So the manufacturer should look back at the tested value in the lab and confirm the required lighting impulse and switching impulse for the required altitude. But of course, in that case, you are just applying a factor on the tested value. The main difference with surge arresters is that you have to refer to a protection level, right? If you compare let's say, the calculation method on the insulator string or on the post insulator, you don't have protection levels. So you need to consider, let's say, standard lightning impulses and standard switching impulses for the required Western voltage. So I hope it's answered the questions. Okay, I go on. So if I'm not answering properly, feel free to contact us, and we will. If you give me a concrete case, we can, let's say, we can go a little bit deeper. Okay, another question. In case you pick up a UPL, so a lightning impulse residual voltage, does it mean that this is the maximum of a voltage you will have in the protection area of the arrestor in case of lightning strike? In other words, you limit the maximum of a voltage due to the lightning with the UPL value. Yes, very good summary. Exactly, this is correct. That's why it's very important to look at the data sheet of the surge arrestor and to look at the different residual voltage for the currents that you need. Normally, we use the nominal discharge current. You can use a higher current if you want to have a safety margin, but typically, this is correct. You are no longer looking at the maximum lightning over voltages, for example. You are looking at the protection level of the arrestor. And it's good that you mentioned protection area. Yes. Okay. Next questions. With the UPL, UPS, so protection levels of the arrestor, UPS values limit the maximum of voltages due to the lightning and switching respectively to the specific values in the protection area of the arrestor, or the over voltage due to this higher. Oh, I think this is coming from the same person. So your understanding was correct. Your understanding was correct. The protection level is the maximum expected of a voltage. But of course, as you can see on the screen, we have some coordination factor also, because we might see higher discharge currents than the nominal discharge current. So that's why you have this kind of this safety margin. Okay. You replied to some questions, Philip, right? That's why it's okay. It's getting smaller and smaller. Okay. Up. Okay. Up. I got another one from, I think, the same person. So there is nonsense to close the UPL to the BIL level, because the possible over voltage will be close to BIL limit, right? I'm not sure if I understand exactly the question. So typically, if we take an example for 245 kV system, a typical BIL for the system is 1,500 kV. If you look at the typical residual voltage for a surge arrestors, let's say, yeah, actually it depends. Let's say 192 kV rated. The residual voltage is in the range of 400, 500 kV, something like that. So there is a significant safety margin between the BIL of the system and the typical residual voltage of a surge arrestor. And as I mentioned, it's always possible to go even below. And I don't understand the wordings to close the UPL. So the idea is the idea, depending on the, of course, the on the challenge you are facing, if it's about altitude, if it's about clearances, if it's about the typically distance, minimum distance in your substation. The idea you want to reduce the distance, therefore you want to make it compact, therefore you'd like to know to know what's the minimum BI level, and in order to know the minimum BI level, you need to know the maximum residual voltage, including coordination factors. Okay, next question, and I think we will be more or less good with the timing. So feel free to ask more questions. We have additional 10 minutes. From Mr. Farouk Genk, is there any distance limit between surge counter and surge arrestor base and surge counter to Earth? How to define these distances? Will you explain this in another session? Yes. Actually, this question is coming very often, so we will definitely make it most probably in the arrestor selection, or I don't know what's the most appropriate session, but this is definitely something, like all the questions are saved and from the last webinars. We will definitely consider all the question that was not answered so far. Just to give you some let's say some information. So in general, I would say surge counters are not. Oh, you remove it. Okay, so we will answer later on. But basically, I would say surge counters are not needed. It depends what you want to do with it. If this is for statistics information, if you want to just measure the number of other voltages, this could make sense. If you really need surge counters, of course, there is a minimum distance between the base of the arrestor and the surge counter. As you know, to make sure that the energy goes to the surge counter, we use insulating bases. And those insulating bases, they have maximum Western voltage. And typically, when you have a very fast front over voltages, so typically a very fast front lightning over voltages, there is, if the distance from the bottom of the arrestor and the surge counter is too long, there is a probability that the base flush over and that the information is not recorded by the surge counter. So typically, values will depend on your insulating base. You have two possibilities. You can increase the insulating base. It's also a possibility if you have this issue. But yeah, I would say the value is in the range of 2-3 meters, roughly, to make sure that the impulse or the lightning impulse or the transient of a voltage goes to the ground. I mean, go to the ground via the surge counter. Yeah. Okay, I have, so I don't know the name. It's anonymous questions, but this is the, let's say the next to the previous question. The next question to the previous question. So if you have 1,500 kV BL and you pick up a protection level of 1,425, for instance, I understand that this is nonsense because the possible over voltage will be close to BL. Yes, you're right. But what is nonsense here is this protection level for such a BL. So such a BL means that you have a system voltage of 550 kV. A typical UPL, so a typical lightning impulse protection level at 20 kA, let's say, nominal discharge current, is not 1,525 kV. Even if you use very cheap varistors, very low quality, you will never get this value. This is extremely high. So a typical value would be 1,000. Typical value with standard MOV blocks. So I hope this answers the questions. Then we have another question from Bastian Abarca, talking about nominal voltages. What is the criteria for choosing nominal voltages? For example, thinking about a system of 550 kV, why should I prefer? Okay, why should I prefer a rated voltage of 420 than 396 for the nominal voltage? Thinking that maybe I need lower residual voltage. Yes. So the wording nominal voltage is not correct. It's if we talk about 420 and 396 kV for a system of 550 kV, we are talking about rated voltage. Maybe I have. Let me check. I just took this slides from previous webinar as an example. Maybe we can. Yes, I think this is the most relevant slide. Okay, so to answer your question, oops. To answer your question, it's important to look at the voltage characteristic. The voltage current characteristic of the metal oxide varistors. So this non-linear shape is always the same for metal oxide varistors, and it's important to split. Actually, I should improve my slides. We don't see it very well, but it's important to split the curve in two parts. On the left side, where you have the operating points, this is going to be in this area. This is going to be the operating, operative area. On the right side, where you have this 20 kA residual voltage, we have this, let's say, this, how should I call it, protection level area, or yeah, lightning transient of a voltage area. The main challenge when you design a surge arrestor, but also when you manufacture metal oxide varistors, is the ratio between your protection level and the operative value. So typically, the rated voltage of a surge arrestor is a TOV value, so temporary over voltage, for 10 seconds with prior duty, which means that your surge arrestors has been pre-stressed to be in the worst case condition. So if you want to increase the TOV capability of the surge arrestor, you need more MOV blocks. More MOV blocks means that you're gonna take this curve and put it higher. More blocks means putting the curve higher, or to move up the curve. So if you increase the TOV capability, you increase the residual voltage. So this is always the big challenge. What do you want? So in your case, if you have a 550 kV system, if you want 420 kV rated, it means that you have some you want to withstand a specific TOV value. So typically face to ground, the surge arrestor should be able to withstand 420 kV face to ground with prior duty for 10 seconds. This is the meaning of the rated voltage. If you use 396 kV, the protection level will be much better, but you need to make sure that you can withstand the TOV. So this is always a balance to be found. And we will go into the details in the next session for the arrestor selection.